how do I? Okay, so share my screen. Okay, do you see my screen now? Is that okay?
Not yet. It just says that you, okay, now we see it.
Yes, we see it now.
Okay.
Okay, but now I probably can say it's a great pleasure to have Jiang-Hua Lu as today's speaker. And here you see the title. So she's going to talk about some examples of algebraic, Poisson, and symplectic groupoids.
Okay. Well, thank you so much. Thank you and for Nikita and all the organizers for the invitation. It's very exciting to give an online talk like this. So can you, okay, is the screen, is the full screen showing?
Yes.
Yeah, okay, great. Okay, thank you. Okay, so I'll talk about some examples of algebraic Poisson and symplectic groupoids over some polynomial Poisson structures on the vector space. Okay, so everything is supposed to be a polynomial. And so this is based on some joint work with my two former students, Victor Mgan and Yu Shizhuo. Okay, so, all right. So just to warm up, I would like to give some systematic examples of polynomial Poisson brackets. So just a very quick review or warm up. Okay, so I'll just do this very quickly. So we have constant Poisson structures or linear Poisson structures. For the quadratic ones and the easiest examples will be the log canonical ones. And then for higher order, in general, it's just not easy to come up with. To come up, you have to, it's artificially coming up with higher order ones is not that easy. So for this talk, I'll concentrate on this, on the following type. So there is going to be, there's one polynomial Poisson structure on CL for every sequence of simple reflections of size L in a vowel group. Okay, so this was a theorem proved, start with my former student, Balash, in his thesis, and eventually was written up and published only last year. Okay, so we'll concentrate on this class. Let me just briefly give a few features of this class of polynomial Poisson brackets. So first of all, it has lots of Poisson subalgebras. Okay. So in particular, actually, it's more than that. So if you for any I less than j between 1 and L, the Poisson bracket between xi and xj has a log canonical term, and that's the only place where xi and xj appear, and then then there's a tail term which only depends on the variables strictly in between. Okay, so this is only term where xi and xj appears. So that's one property. The other property is that it has a natural torus action by Poisson automorphisms, and it has finite many T leaves. Now T leaves is a notion that I'll explain very quickly in a little bit. And since there are only finite many T leaves, so one of them is open. So there's an open T leaf. So that's another striking property of this class of Poisson structures. And one can compute this by computer program. So this all depends on so this vowel group is the vowel group for some simple Lie algebra. So it depends on the structure constants of the Lie algebra. So you can put all of that in the computer. So Balash actually wrote a computer program for computing. So the input would be just the type of the vowel group. Okay, so let me just give you some quick examples. For G2, we know that G2, the vowel group is the dihedral group of 12 elements. It has 6 generators. So suppose I choose the sequence to consist of 6 elements. So 1, 2, 1, 2, 1, 2. And this gives a Poisson bracket on C6. Okay, so here is what it is. So let's note, for example, like the bracket between x2 and x6. So it has a log canonical term. And then this other term involves only x3, x4, and x5. So that's the first property. Okay, so next I want to double the size. So here is six dimensions. So we go to 12 dimension. So we start with the original 1 2 1 2 1 2. That I'm going to add 2 1 2 1 2 1. So this is like the reverse of the previous one. Okay, and then so I get a Poisson bracket on C12. And here are some. Now there are many Poisson brackets. So I just give a few, just show a few. You can see, for example, that between 3 and 10, you have a log canonical term. Then you have all these other terms involving only the variables in between. Now, this example has a special property that it has an open symplectic leaf. This open symplectic leaf is defined by setting two particular polynomials to be non-zero. So it's a Zariski principal, Zariski open subset. And these two polynomials it's very long. I'm not going to write them down because like involving 12 variables is very, very long. But they have Lie theoretical meanings, and then it's actually very nicely defined. So now already, I mean, if you like get bored for the rest of the talk, I can roughly say, whoops. So this particular one, this 12-dimensional one, is almost the symplectic groupoid of this previous one. Oops. This 6-dimensional one. So the goal is to construct symplectic groupoids for let's say the 6-dimensional Poisson structure on C6. And then the answer is that it's almost this one. Okay, now this one is the open symplectic leaf. This is almost because actually for a while we thought that this would be the answer. And that would be very nice because this guy is everything again is very explicit. It's twice the dimension, it's symplectic. It also has a groupoid structure, but turns out that that's not, we just couldn't, for a long time, couldn't prove it. Eventually then the answer is that this is not the symplectic groupoid, but the final answer is that the symplectic groupoid is a finite cover of this one. Okay, so that's what I'm going to explain. So for today's talk, I'll first give some backgrounds of these polynomial Poisson structures. I think many of you may have heard some of my talks where I talk about these polynomial Poisson structures, but mainly I'll talk about the symplectic groupoid, constructing the symplectic groupoid. Okay, so first of all, I'll have recall some basic concepts, and then I'll give a very general construction. It's a very strikingly general construction, very simple also. And then I'll apply this general construction to one example. One particular example, I'll get my groupoid. Okay, now just then in the last part, I want to give some remarks. So I call this in the whatever scale scheme of things, because yeah, I want to put this construction in perspective, like how this is related to some other topics. Okay, so part one, basic concepts. This will be very first of all, T leaves. So this is a very simple concept. So if you have a torus, so a T Poisson manifold by definition will be a Poisson manifold with a T action preserving the Poisson structure. Okay, all right. And then if you have a T Poisson manifold, a T orbit of symplectic leaves, or we just call it T leaf for short, is a submanifold of this form. You just take one symplectic leaf, you let all the torus elements act on it. You sweep out, you perhaps get new symplectic leaves, or maybe still the same, you union them. So this is a toric orbit of symplectic leaves. And then I add a technical condition. I want this map to be a submersion. Okay, so this is the notion of T leaves. Okay, so the second concept is that of mixed product Poisson structures. Okay, so if I have a product manifold and then have these projections, so a Poisson structure on the product manifold is called a mixed product if the projection to each factor is a well-defined Poisson structure. So it's a very simple definition. Okay. Now this is, of course, this is equivalent to if you pull back the functions on each vector is a Poisson subalgebra. Okay. So locally or in coordinates, suppose you only have two, like x cross y, and then the Poisson structure should look like this. Like the first copy is just the first part is just the Poisson structure on x and another Poisson structure on y, then you have a mixed term. Okay, so in general, when you have, in general, in this term that has ddx, ddxi, ddxj, these coefficients, in general, for an arbitrary Poisson structure, the coefficients may depend on x and y. So this alpha ij could be a function of x and y. So here we only want it to be a function of x. Okay, so that's the property. So this is called the mixed product Poisson structure. Okay, third concept would be, of course, this is well known to most of the people. So Poisson groupoids and symplectic groupoids. So I'll recall this very quickly. Poisson groupoid is a Lie groupoid with source and target map called theta plus, theta minus, with a Poisson structure that's compatible with the group multiplication in the sense that the graph is a coisotropic submanifold. And in such a case, then we know that the source maps and both the source and the target maps map the Poisson structure on gamma to well-defined Poisson structure, and they coincide after a minus sign. And then so that's called pi m. So then I denote the Poisson groupoid as, so I put the Poisson structures in to indicate the Poisson structures involved on the base and the total space. And then the symplectic groupoid is a Poisson groupoid where the Poisson structure on the total space is non-degenerate and twice the dimension. Total space is twice the dimension. Okay. And then, so then it's a basic problem in Poisson geometry to construct interesting Poisson groupoids and interesting symplectic groupoids. Okay. All right, so this is part one, basic concepts. So I talk about three basic concepts: T-leaves and mixed product Poisson structures and Poisson and symplectic groupoids. So that finishes part one. Okay, so part two, I will talk about a general construction. So this is a very general construction. So first of all, I recall some examples of Poisson groupoids. The first one will be the pair Poisson groupoids. If you have a Poisson manifold, you can look at the pair groupoid becomes a Poisson groupoid with pi x cross product with minus pi x. Okay. The second one is a Poisson Lie group. So a Poisson Lie group is a Poisson groupoid over a one-point space. Okay, so now I'm going to combine these two examples to construct what I call the gauge Poisson groupoid. So for that, I recall a Poisson action of a Poisson Lie group is a Poisson map, which, so from the product, so x cross g, product Poisson space to x, which is also a right Lie group action. Here I'm talking about right Poisson action. And in such a case, you can form quotients. Quotient Poisson manifolds can be formed by quotienting out coisotropic. Oh, sorry, I forgot to write down. Sorry, I missed a line. So Q is a coisotropic Lie subgroup. Okay, so this Q is not necessarily the whole G, doesn't even have to be a Poisson Lie subgroup. It's just a coisotropic subgroup. Yeah, sorry, I forgot a line. Okay, and then the Poisson structure is just the projection. So Q being a coisotropic subgroup makes the projection well-defined. Okay, so I call this a quotient Poisson manifold. So you can have many, every time you have a quotient, you have a coisotropic subgroup, you have a quotient. So that's all I need. So now I'm going to define what's called gauge Poisson groupoid. All right, so I start with a free proper Poisson Lie group action on the Poisson manifold. It's a proper action, so I can talk about the quotient. So X quotient by G, so that's with a quotient Poisson structure. And then I can also take the quotient by the diagonal action on X cross X. Now, if you give X cross X this product, X pi X product minus pi X, now that has a Poisson action by G cross G, but the second copy of G, you give it the minus negative Poisson structure, and then the diagonal becomes a coisotropic subgroup. So therefore the quotient has a well-defined Poisson structure, okay? So the quotient by the diagonal action has a well-defined Poisson structure. And then you take the gauge groupoid. So the gauge groupoid, by definition, is just the quotient manifold by the diagonal action. Then it has a source and target, just given by this. So the square bracket denotes the equivalence class on the quotient space, in the quotient spaces. And then now you can see that it's just almost a pair. You look at the definition, it's almost just a pair groupoid, except that you have to look, you should be looking at conjugacy classes, sorry. And then, yeah, for the multiplication, you need to be a little bit careful. Yeah, so then the statement is that this is a Poisson groupoid. So the proof of this fact is very simple, but I have not been able to find a reference. So I don't know whether anybody has a reference for this, whether this fact should have appeared somewhere. Okay, so it's very simple. You have a principal bundle where the action is by a Poisson Lie group. Total space is a Poisson manifold action by Poisson Lie group. And then this claim is that the gauge groupoid has a, with the quotient Poisson structure, is a Poisson groupoid. So I don't know anybody knows whether this has a reference for this statement. Okay, so that's the general, so that's what I call the gauge Poisson groupoid. And now I'm just going to apply this to a particular case. So this is, I call the general construction 1. So then I have a general construction 2, then combine them will be my general construction. Okay, so the second part of the general construction is a series of quotient Poisson manifolds by starting with a closed Poisson Lie subgroup of a Poisson Lie group. Okay, and then if the Poisson Lie subgroup acts on by a Poisson action on the Poisson manifold, then you can form this quotient. Okay, so this G cross Y quotient out by the diagonal action of Q. Okay, so it's the same story as before. The diagonal Q is a coisotropic subgroup of 2 copies of Q with a negative Poisson structure on the second copy. Therefore, this projection is well defined. So the product Poisson structure on G and on Y projects to a well-defined one on this quotient. So I denote this quotient by this way, okay? So put the Q in the middle. This is just one-step construction. Now you can just form this consecutively. So if you have a sequence, if you have several let's say n closed Poisson Lie groups, then you can form the successive quotients. You can start with G mod Qn. So in my example, the Qn could be the trivial subgroup. So it'll be only starting with G. And then you can do this, right? So use Qn minus 1. So this will be your Y. So this G mod Qn will be the Y. And then you form this one. And then you can do the next step. So this whole thing will be your new Y. And then you can just quotient and quotient and quotient. And then eventually you get this one. Okay.
So these are nested subgroups or not?
No, they are not related.
Okay.
They don't have to do with each other. But in my example, okay, so now this quotient, in my examples, I'll have Qn to be identity, and all these other Qs will be the same, or this one, or they are all the same. So this will be the main example. So if you want to have this quotient in one strike, you can do that. So you can think of this as a quotient of n copies of G by this product group, where the action is this kind of action. So I put all these steps into one step. So what I get is this overall quotient of Gn by this product group. And then the statement is that because this is a one successive quotient, so that you get a Poisson structure on this quotient space, which is simply just a projection of this product Poisson structure on G. So the statement is that the projection is well-defined, is a well-defined Poisson structure on the quotient. So whenever the quotient, if it's denoted by Zn, I'll denote the Poisson structure by pi, the subscript Zn. So that is what I call the second part of the general construction. So now I'm going to combine. So remember the first one construction was about the Poisson, gauge Poisson groupoid. So I'm going to combine that construction with this construction to get, so combine these two, and this will be the summary of what I call part 2, the general construction. So all you do is that you start with one closed Poisson Lie subgroup, Q, okay? And then I can form all this. So in this one here, you see the Qn is identity, all the other Qs they're all the same. And then in this one, they're all the same, okay? Now what happens here is that if you look at X2n, so you take 2n copies of G, you split that as the first n copy and the last n copy. And then you see what's going on is so the first one, so this whole bunch gives you xn, and this bunch gives you another xn, and then you're doing the diagonal action. And xn is so I can then apply my gauge groupoid, gauge Poisson groupoid construction, right? So combine, so use the gauge Poisson groupoid construction in the first part of the constructions. I get a Poisson groupoid. So this is the if you unravel the gauge Poisson groupoid, gauge groupoid structure, you see something like this. So this is just the detail of the structure maps.
Maybe ask one question.
Yeah.
Since you're saying gauge groupoid, it looks a little bit like moduli space of flat connections and acting by some gauge transformation. Is there some actual geometric interpretation?
Most likely, and Eckhart, I think, I think I'm sure this I just don't know how to speak in that language, but I'm sure, because this type of actions always appear. Yeah, I don't know whether like Pavel Schwera is in the audience, and he probably will give me a picture and then say this is all. Yeah, he can give a picture, a proof of everything I'm going to say, maybe. Yeah. Okay. Yeah. Also, the name Poisson gauge groupoid, I'm not sure that seems to be a reasonable term. Yeah, if any of you has seen it somewhere, yeah, I would love to see a reference, right? But if you see this, yeah, so these details of this groupoid, this is also very, very interesting. You see, it's very, yeah, it's kind of nice. I was sort of shocked. So you see where I start. All I start is a Poisson Lie group is a closed Poisson Lie subgroup. Okay. What I get is a series of Poisson groupoids. Okay, so the base is this type of, so the base is this Yn, the successive quotients by Q, and the total space is just, yeah, is just that. Okay, so this is the second part. This is what I call the general construction. Okay, so next, part 3, I'm just going to apply this construction to a very concrete example. So this very concrete example would be this so-called semi-simple, standard semi-simple complex Poisson Lie group. So I start with all of this familiar data. Have a complex semi-simple Lie group, fix a pair of Borel subgroups, and then maximal torus and Val group. And you also need an invariant symmetric non-degenerate bilinear form. You can take the Killing form, for example. And then it's well known that all this data would give rise to a standard classical R matrix, and therefore a Poisson Lie group, where this ST, so it's the R matrix left translate minus the right translate of the R matrix. And then this ST stands for standard. So I always use pi ST. The standard versus the other, like Belavin-Drinfeld type of R matrices. So this is using the standard one. The standard one is such that has the property that both B and B minus are Poisson Lie subgroups. Okay, so therefore I have my pair now. I have my Poisson Lie group. So my Poisson Lie group is the standard complex and simple Poisson Lie group, and then the Borel as the closed subgroup. Okay, so then I'm going to apply the construction in part 2 to this pair, and then I get a series of Poisson groupoids. Okay, so all right, so now it's because so this has to do with flag variety, so I changed the notation. I call this Fn and F2n tilde. Okay, for some reason. For that general construction, I just called Xn or Yn and so on. But for this particular example, this has to do with flag varieties, so I'll call this Fn. Okay, and then it has this quotient Poisson structures. Now in this, I'm going to introduce a particular subvariety. So F2n, so the subvariety. So first of all, there's a well-defined product map, because the way that this quotient is defined, if you multiply all of this, is well-defined. Okay, so this is called gamma 2n, and then so this is just direct application of part 2, except for this last sentence. So I did not write down, copy all this. The groupoid structure is precisely as in the previous on the previous slide, where for the general case. But this now it has a very distinguished Poisson subgroup. I think the word this wide Poisson subgroup, wide subgroupoid. I think what I mean by that is the it contains the identity section. Is that the definition? Is that right? Okay, so this one gamma 2n is a wide Poisson subgroupoid. So it's clear that it's a wide subgroupoid. The statement here is a Poisson submanifold, and it's a subgroupoid, so it's a Poisson subgroupoid. Okay, so once again, applying the general construction in part 2 to this particular example, I get this sequence of a series of groupoids, Poisson groupoids, but then I'm going to concentrate on this one of its distinguished Poisson subgroupoid. So for today, the main topic for today will be on this. So for each n, so this thing in red, so this is a Poisson groupoid for each n. Okay, so let's just recall that this Fn is this sort of weird product, is quotient, and gamma 2n is this, yeah, so the product has to lie in B minus. Okay. All right, so what do I want to say about this? Now, since this one is so important and I think it's very interesting, so I'm going to try to give it a name. I want to give this groupoid a name. I'm not very successful in doing that, but I'll try to explain. I don't quite have a very good name, but I'll try to explain what I want to call it, why I want to give it that name. So you have, so the B, the Borel B has a unipotent radical. So in the case of SLN, the B will be all upper triangular matrices, N will be strict upper triangular matrices. So the F1 is just when you have one copy, N equals 1, this is just G mod B, and this is well known to be just the flag variety. And the Poisson structure is just projection. And then you have G mod N. So this is called the decorated flag variety, sometimes also called the base flag variety. It also has the projection Poisson structure coming from the coming from G. So it's the projection Poisson structure. So now let's take an open subset. So A naught is this open subset defined by this way. Okay, and then as varieties, so this gamma 2n, which is this the total space, that the total space is actually isomorphic to 2n minus 1 copies of flag variety times an open subset of this decorated flag variety. By this map is a well defined map. You just successively multiply the elements. So first G1, and then G1, G2 multiply, then G1, G2, G3. If you multiply up to Gn minus 2 and minus 1, you are still in the flag variety, but the last piece lies in B minus. So you think of this as defining an element in A naught. Okay, so similarly, the base is isomorphic to n copies of the flag variety by some map that's similar. Okay, so since these are variety isomorphisms, I can push the Poisson structure to the other varieties. Originally, they are on gamma 2n and Fn, but I just use the isomorphisms to push them to the other varieties. Now look at these other two varieties. You can think of these are just sequence of flags. In this case, the last flag is kind of special. You call that a decorated flag. And then this Fn is the sequence of all flags. So these spaces tend to be called configuration spaces of flags. I mean, here is just the total, just all sequences of flags. So therefore I call, so I have a groupoid structure on here. I can use the isomorphisms to push it as a groupoid structure on here. I want to call, I don't have a, as I said, I don't have a very good name, but I call this the nth flag configuration Poisson groupoid of G. For at least temporarily, I want to call it just a configuration Poisson groupoid. Now you notice that this is completely canonical. And this groupoid does not depend on anything. The groupoid does not, just as you have, just like you have a flag variety, that you have this sequence of groupoids over these products of flag varieties. Now the Poisson structures come in when you have this, when you equip G with a standard Poisson Lie group structure, then these groupoids naturally become Poisson groupoids. Okay, so this is the, as I say, this sequence of groupoids are very natural. So I try to give them a name. Okay, so then if you want, for example, then you want to ask, like, this Poisson structure is kind of mysterious, sort of. It's not, I mean, the way that it's defined on gamma 2n is just a projection. But if you think of them as Poisson structures on this product space, the statement is that they are mixed products. So the concept that I recalled at the very beginning, these are mixed products of n copies of pi 1, for example, the one on the base, because this is a product. Each copy of B has this Poisson structure pi 1. And so this is a mixed product. So you have mixed terms. It's more than just the mixed product. According to the definition I gave, is actually more special than that. But I don't want to go into the detail. So both are mixed products. Okay. So this is the as I say. So this is the. So I want to say more about this groupoid. So about the base of this configuration groupoid. So the base has a canonical decomposition, which is given by the Broha decomposition of the group G. So Broha decomposition of the group G is indexed by the vowel group. And then so you do it from on each copy of G, and then you get on Fn, you have this decomposition. And then it's not hard to prove that each piece is a T Poisson submanifold. The statement now is that each piece is interesting. So each piece OU is in fact a vector space. It's just affine. It's not only an affine variety, it's just affine space. It is a copy of C to some power. Now this depends on the length of this vowel group elements. Okay, so therefore, so now how do you make this parameterization? You have to use the root subgroups and the reduced words of UI. So I'll skip the detail. Using that, you can find an isomorphism. Okay, so therefore you get use this inside these coordinates of parameterization, you get polynomial Poisson structures. Okay, so once again, so each guy here, OU is a Poisson submanifold, is isomorphic to C to a power, and then therefore you get polynomial Poisson structures on C, on this vector space C. So this is the one that I talked about at the beginning. At the beginning. Okay, so I give this some names. So OU is called a generalized Schubert cell or Broha cell. So generalized because in the case when n equals 1, we just get the Schubert cells. So now I just call this a generalized Schubert cells. And then the restriction of the Poisson structure on Fn to the Schubert cell, so I call that the standard Poisson structure. Standard because it comes from the standard Poisson structure on G. Right, so and this coordinates, and so this identification give coordinates, I call those, so those are called Bott-Samuelson coordinates. Okay, so these are just some terms. Now the beginning, the example of G2 that I gave earlier on, so the 6-dimensional and the 12-dimensional, they are just examples of this. Okay, so those are the in Bott-Samuelson coordinates, and they become, I get a polynomial Poisson brackets. So that's an example. So what I talk about at the beginning is an example for generalized Schubert cell for G2, or actually 2 examples. Okay, so this is about the base. So this is about the base. So now I can actually, so remember that the goal of the talk is to construct symplectic groupoids of the Schubert of this polynomial Poisson brackets. So I have explained what the geometrical setting for this polynomial Poisson structures. So that was the goal. So let me just briefly give you a very brief some history. For n equals 1, this Schubert cell is lies in the Fleck variety. So Victor and I, we actually give a proof. We prove that the so-called double Broussard cell is actually a Poisson groupoid. And the symplectic leaves of the double Broussard cell are symplectic groupoids. So this was actually the beginning of the project. First of all, this is only for n equals 1. And then here, what we use are so-called double Broussard cells. Okay, and then Victor wrote a paper more recently where he showed that the so-called generalized double Broussard cells. So we can define generalized double Broussard cells is the Poisson groupoid over this OU, over the generalized Schubert cells. Okay, but then there was no statement on symplectic leaves. So I want to say just a little bit more this in many ways. So here, to make the generalized double Broussard cell into a Poisson groupoid, you need to make a choice. The choice is the representatives of the Weyl group elements appearing in U inside the group G. You need to choose representatives of the Weyl group elements in G. Okay, so for different choices, you get a different groupoid structure, but then they're all isomorphic, but still you have to make a choice. Okay, now the reason that Victor could not, in his paper, he did not make any claims on the symplectic leaves being symplectic groupoids was because in general, so this is the general phenomena for these Poisson structures related to the standard Poisson Lie group is that the T leaves are always easier to determine. And very often there are only finitely many, but the symplectic leaves are a bit harder a bit trickier to get. Okay, so all this GUU and all of these are single T leaves. But then so the issue was to figure out what precisely the symplectic leaves are, and that is actually a harder question. So that's just a little bit history. So now I can already finish so let me just give the result. So what we are looking for. So remember that we have this configuration Poisson groupoid, okay? And then, so the base now has this decomposition into Schubert cells, okay? And then, so what do we do? Remember that I want to get symplectic groupoids of each piece. I have a Poisson groupoid on the whole thing, okay? Fn is a union, disjoint union of pieces. I want to get a Poisson symplectic groupoid of this piece. So then what is the natural thing that I do? Then you take this so-called, I think this is the term, I'm not sure, is this the term, wide subgroupoid over OU? By definition, is just take the pre-image by the source and target maps and intersection. So this is automatically a groupoid over OU, right? So I'm not sure, is this the right term? I think this is the wide subgroupoid. So whenever you have a groupoid and you have a subspace of the base, you can always do this construction, right? You get a groupoid. Is this Alan, is this the right term?
I think so. Well, as you said earlier, wide means that it contains all the identity elements. I mean, yeah.
Right,
so
but here I have
the image of the source and target are the whole space.
Right. No, but here, see, I have a groupoid over something, and then I take a subset of the base.
Mm-hmm.
Then I take a subset of the base, and I just do this construction. Then I get a groupoid over the subset.
Yeah.
Yeah, I don't know. Is the term wide?
Yeah. So wide means that the image of the source or target map equals the whole space.
I think this is full. This means a full groupoid.
Full. Is this called full subgroupoid?
I think both terms are used.
Oh, so full subgroupoid. Okay, thank you.
You're welcome.
Okay. Okay, so right, yeah. But in general, you can, okay, so in general, if you have a Poisson groupoid, and then, so on the base, you have a Poisson submanifold, even if you take the full subgroupoid over that Poisson submanifold, in general, it may not be a Poisson subgroupoid, I think. So now here is actually, here is the theorem. So first of all, this is a fact that the total, so this gamma u is a single T leaf. I forgot to say that this whole thing has finite many T leaves. Okay, so this gamma u is a single T leaf, so therefore it's a Poisson submanifold. And now it's also a Poisson, is also a subgroupoid by definition. So therefore is a, oops, what happened? Yeah, so therefore it's a, yeah, so the first statement is that it's actually as a Poisson groupoid. So the second statement is that the symplectic leaf of this groupoid through the identity section is a symplectic groupoid. And then third statement is that the double Broussard groupoid that Victor got, they are just all isomorphic to gamma u, to this Poisson groupoid. The isomorph, because you have to make the isomorphism, you have to make a choice of the representatives of this Val group elements. That's why Victor has many of them. That's because you have many different Poisson isomorphisms, and they all up to some torus action. Okay, so I'm not going to talk too much about this GUU, but I want to concentrate on part 1 and part 2. I find this rather amazing in general. I don't know of whether any of you knows of a situation like this in some other cases where, so what I have is that I have a Poisson groupoid over, I have a Poisson groupoid. Now the base is the disjoint union of pieces, and each piece is a Poisson submanifold. Okay, so all I do is that I take the full subgroupoid or full or wide subgroupoid over each piece. Then what I get is a Poisson subgroupoid. I get a Poisson groupoid over each piece. And then the symplectic leaves through the identity section is a symplectic groupoid. So this is a rather nice situation. So I think in general, if you have a Poisson groupoid, and for example, if you take the cotangent bundle as the symplectic groupoid over the base with 0 Poisson structure, you take a point, which is a Poisson submanifold of the base. The fiber, I mean, the fiber is a Lagrangian, is not a Poisson submanifold. So that's not, so this is a very striking case where this happens. Right, so this is already the, so I have already answered the, I have already achieved the goal that I started with for the talk, which I said at the beginning, I said I wanted to construct symplectic groupoids of this class of polynomial Poisson structures. So here the same here, so here is the construction. Right. Okay. So except that I want to say a bit more about these groupoids. Okay. So the next question. So I'll just the next question I just want to say is why these things? What kind of Poisson manifolds they are, and what kind of properties they have. So this is my part 4. This is the remarks. So why are these Poisson manifolds or groupoids interesting? So this OU pi n, remember this is the generalized Schubert cells. So first of all, I want to say from this point of view that generalized Schubert cells are building blocks, basic building blocks. So I want to explain what do I mean by this. So first of all, remember, so once again, so these are under Bott-Samuelson coordinates, they are just the polynomial Poisson structures on Cn, okay? Striking properties. This is because first of all, we have this decomposition, and I have already shown proof, explain this to you, that this space here is this is a projective variety, projective, compact, and everything. But then it has the cell decomposition, and so each cell is a generalized Schubert cell. So this is in a Poisson way. So this is, I call this like a paving of this projective variety into by generalized Schubert cells. So this, in this case, they form pieces. And then there's other examples where this is some recent work of me with my student, former student Yu Shizhuo. So many Poisson homogeneous spaces, for example, like G self or G mod B or G mod T with the quotient Poisson structure, they have open covers. So they are covered by this generalized Schubert cells. So that's another very striking property, or this is where the Schubert cells, generalized Schubert cells show up. It's not quite, so this is by some kind of T mixed products. Okay, so there's some twist there, but basically they're products of Schubert cells. So these varieties are all covered. That's different from paving. Okay, paving means it's a disjoint union, but cover, this is a genuine cover, open cover. So by these things. So this is what I mean. These are two incidences where I see this generalized Schubert cells are building blocks. Okay, so understanding them would imagine that you have a, well, anyway, we just, so there's a so we just so this paper is on the archive. It's going to appear, so yeah, so I probably don't have time to talk. There are lots of consequences of this result. Okay, so the other thing I want to emphasize is that there's a very prominent feature of these varieties, which is this what I alluded to at the beginning of my talk. So for that, I need to explain what's called the symmetric T Poisson CGL. So this is a concept introduced by Goodall and Yakimov. The CGL, these are the name of three mathematicians, Poisson, Goodall, and Lester, I think. Yeah, okay. What are these? So these are polynomial Poisson algebras, okay, with a T action by Poisson algebra automorphisms. So first of all, they're polynomial Poisson algebras with a T action with two more properties. First of all, so each of these coordinates is a weight vector, okay, with a particular weight. And then you can also, so this is a little bit technical. So you have elements in the Lie algebra of the torus with this non-degeneracy condition, such that this is property I explained at the beginning. I showed you some examples of this. So you have the log canonical term plus a tail term. The tail term involves only the variables strictly in between, and then xi, xj is a log canonical term. So the whole point here is that the coefficient of the log canonical term is given expressed using the torus action. So this is what's called the symmetric T Poisson CGL. Okay, so this is it's strikingly, I think it's a very, very special class of polynomial Poisson algebras. And once you have this, you can do some extension by the torus or by by another copy of another vector space where you just extend the Poisson bracket log canonically. So on the coordinates of T, just the Poisson brackets is all 0. Between the xi's and the coordinates on T is log canonical, okay? So you can do this and the result is again a Poisson CGL. Now what I mentioned, the properties of this Poisson structures on the generalized Schubert cell, so I can say it in one word, is that what you get is a symmetric T Poisson CGL in about Samuelson coordinates. Okay, so now why is this interesting? I'll say a little bit later on, but so yeah, so the statement is, so that when I first mentioned in the second slide, when I mentioned this polynomial Poisson structures, I said they have finite many T leaves, and then their Poisson brackets have these properties and so on. In one word, you can summarize all of those properties in this one word, which is that they are symmetric Poisson CGLs. Okay, now, so then the next question is, if the base OU that you're trying to integrate to a symplectic groupoid is a Poisson CGL, has all these nice properties, how about the total space for the symplectic groupoid? Okay, so basically I want to say that this gamma U or its symplectic leaf is of the same kind. They're also Poisson CGLs. In other words, they are also this belong to the same type of Poisson algebras. But it's not quite, you have to say a little bit, you have to, so let me just give you this whole slides. So basically, so remember I said, so remember that starting from U, I double it, I double the size. So the U inverse, it just reads the U backwards, taking the inverse. And so then, then for that doubled Schubert cell, generalized Schubert cell, it has an open symplectic leaf, okay? And then you can do a T extension, okay? So that's again, you can, this is like a special localized Poisson CGL. And the precise statement is that the total space of the Poisson groupoid gamma U is isomorphic to that, okay? So it's not quite the original Schubert cell, but it's a T extension, okay? And the symplectic leaf, under this isomorphism, the symplectic leaf becomes a finite cover, okay? So that is by projection to the first factor. So this is the final, this is the, so once again, so the statement, then you can also say that like gamma U is a localization and sigma U is a particular specialization of Poisson CGL. Okay, so roughly, so maybe in rough words, then they are all CGLs. Okay, Poisson, symmetric Poisson CGLs. You have to take care of some localization, and then, so the defining equation for sigma for the symplectic leaves are written down explicitly using some information about the Poisson CGL. Okay, so that is the, so that's the second property. What I want to say about, so the first one I said that this generalized Schubert cells are building blocks, and this, so this statement says that these are very special, they are Poisson CGLs. So I want to give this example now. For the G2 example, so remember that I have a Poisson structure on C12, okay, by doubling this the 6-dimensional one, and I have a symplectic leaf given by setting the two polynomials to be non-zero, open symplectic leaf. Then I extend it to C14. Now the 2 is because the dimension of the maximum torus is 2, the rank is 2. Okay, so then everything is again polynomial in a very special way. And then the gamma U is just this Zariski open subset. Okay, so that's the total space of the Poisson groupoid. The symplectic leaf is given by these equations. Okay, so the symplectic leaves is given by these two equations. So it's a 4-to-1 cover of the open symplectic leaf. Okay, so as I said, originally I wanted, for a long time, we thought this guy would already be the symplectic groupoid. And we couldn't prove that for a while, for a long while. And then eventually what we realized now is that the symplectic groupoid is actually a cover, a finite cover of this one.
How do you know the number of sheets of the cover?
Number of sheets is 2 to a power. Yeah, it's a 2, yeah.
Is it always a Galois cover, a principal cover, quotient by a group?
It's a quotient by, exactly, it's a quotient by a 2 group. Yeah.
Thank you.
Yeah. All right, so now very quickly, I'm already at the end of my talk. So in connection with cluster algebras, now the reason for Good or Yakimov to introduce this Poisson CGL, so they have this very striking theorem, which says that every symmetric T Poisson CGL extension is naturally a cluster algebra, okay? So the cluster algebra, also the C's are all so-called T Poisson C's. So for every cluster, all the cluster variables are weight vectors for the torus action, and the Poisson brackets between them are log canonical. So that's what, so this Poisson structure, so that's part of, that's the Good or Yakimov theory. Every time you have a Poisson CGL, you get a cluster structure on that Poisson algebra. Okay, and then there's a paper by Linghui Shen and Wang Daping, where they define certain configuration spaces of flags, what they denote by conf VE, where V is any element in Wn. And then they show that they are cluster varieties. Okay, so the relation between that and ours is that our gamma U is one of their configuration spaces. Well, this is not surprising. I already said that we're dealing with configuration spaces. Yeah, okay. So that is the relation. I don't want to talk, because then to talk about cluster algebras will be a whole other talk. So I just want to say that all the ingredients are there. So all these varieties I'm talking about are cluster varieties. And then in connection with integrable systems, there was a theorem that another former student of mine and I also, so we proved a theorem. So this appeared in a constant volume, memorial volume. It says that there is a completely integrable system on this symplectic leaf where all of its Hamiltonian flows are defined on C. So they all complete. Hamiltonian flows are complete. And they are also very special. You can write them down explicitly. Yeah, I don't have time to talk about this one either. So our symplectic groupoid is a finite cover of this one. So you can pull back all those Hamiltonian functions, and you also get a complete integrable system on our symplectic leaves. Okay, so I think I'm done. So I just want to give a summary of today's talk. My first construction, very general construction, I start with a Poisson-Lie subgroup of a Poisson group. Okay, so that's all I need. Then this would give rise to a series of Poisson groupoids. So that's part one of the construction, general construction. Apply that to this special case, the Borel subgroup being a Poisson-Lie subgroup of the standard Poisson-Lie subgroup, Poisson-Lie group. Complex and simple Poisson-Lie group, I get what I call the configuration Poisson groupoids. Yeah, maybe flag configuration Poisson groupoids. Then I do this most general thing that the base of this one is the disjoint union of this generalized Schubert cells. Okay, and then I take the wide. So each one here gives rise to a polynomial Poisson algebra. Okay, I wanted to find the symplectic groupoids of this guy. So what I do is that I simply take the wide subgroupoid over each OU. And we know that as it's a single T leaf, and then it is a Poisson. So the main result was that it's a Poisson groupoid, and it's one of its symplectic leaves. The leaves through the identity section is a symplectic groupoid. So that's the one that we're looking for. So that was the construction. So this is a summary of the construction. Now the properties of this, so I wanted to again recall, this is my last part. So in this talk, I explained that they are algebraic Poisson symplectic groupoids, right? They are algebraic because they're all defined by equations, and all the operations are algebraic. And then they have this striking property of being localizations or specializations of this very special class of Poisson structures, which are called symmetric Poisson CGLs. And then through the good early Yakimov theory, or Shen and Wang, and we know that they are Poisson cluster varieties. So they have this first special properties, they are Poisson cluster varieties, and they have integrable systems. And not on the integrable systems, the flows are all complete, all defined, the integral curves are all defined over C. Now there are also a systematic way of quantizing this, actually more than one ways of quantizing. It's interesting to figure out how they are all related. So there's a quantization. Okay, so in case somebody asks, I put this final remark here. The groupoid, I explained that the groupoid coming in a very natural way, but there's another way of describing the groupoid structure. It's actually a subgroupoid of something extremely simple. You take the pair groupoid, oops, this is a typo, pair groupoid and this group, product group. So think of that as a groupoid over one point space and take the product groupoid. Of course, that's not my gamma U, that's not my groupoid, but my groupoid is a subgroupoid of that. So it's a subgroupoid of something totally trivial. But that subgroupoid can be written down by equations, so explicit equations, okay? So the very natural question now is, how are all these structures related? How do they interact? On the same stage, all of these different aspects, how do they relate to each other? The quantization, the integrable system, the cluster structures, and the groupoid structure, how do they all interact? And so that will be I don't know all the answers. I know some of them. Anyway, so that's the end of my talk. I have in the last slides, I have a reference for, I have all these references for, yeah. So I don't know how to quote. In the middle of the slides, I don't know how to quote the paper. So there's the end. I put down all these references. Anyway, so that's the end of my talk. Thank you.
Yeah, thanks a lot. So yeah, we can have some questions.
Yeah.
Maybe I'm going to start with a question. So you have these groupoids gamma 2n over fn. Are the groupoids for different n's also related to each other? I mean, are there maps between them?
Right. There are lots of projections. Yeah. Right. The projection, you can always, yes, there are projections. But how are they groupoid morphisms? Maybe they're groupoid morphisms. So yeah. You can always project to the first.
Yeah, I was kind of thinking if there's maybe some kind of simplicial structure going on, that there are all kinds of projections and inclusions and.
Yeah, this remember on the base they are also all related by projections. I'm sure, yeah, but I don't know how to say precisely. But yes, they're all projections. Right. Yeah.
I got another question.
Yeah. Anton. Yeah.
So you mentioned there are several ways to quantize things.
Right.
So what are they? Like, one can imagine quantum groups and class T algebras, or
right. Quantizing. So here you see my student. He wrote down because these are symmetric Poisson CGLs, and he wrote in his thesis, he wrote down a method of quantizing any symmetric Poisson CGL into a quantum symmetric CGL. Okay, one can apply that. And then Victor has some, because these Poisson structures are mixed products. Victor has a scheme of how to quantize mixed products. And then there's in the Eddinghoff-Karsten, they have a notion of what is it called, locally factorized algebra. So which is basically a quantum version of non-committed version of mixed products. Mm-hmm. I think Victor has a scheme of how to quantize such things in general.
But there, how is it, this mixed part of the bracket, it should be defined by the R matrix, I guess.
That's right. That's right. Well, right? Yeah, I mean, like in the G star, like the group G star, you have a B and B minus, right? Roughly B and B minus. And what's the bracket between B minus and B, right? That type of thing. And so when you quantize, you use the R matrix to quantize. That's exactly all these mixed products that I've been talking about. The mixed terms are defined by the B action and B minus action, which is the classical R matrix, but the quantum level will be the quantum R matrix. Mm-hmm. Yeah. So you would quantize that way. And then there's also, you can also quantize this as a cluster variety. You look at the quantum cluster algebra. That's another way of quantizing. Yeah.
And all these ways, they give the same or not necessarily?
Oh, I don't know. That's the question. Mm-hmm. Okay. I would love to even understand one of them perfectly well, very well. So to be able to be very precise. Yeah. And then the other thing is these integrable systems, how they come into the, yeah, the flows are very strange, are very special. Yeah. Mm.
Okay, thank you.
How do you prove that they are integrable? Use by Hamiltonian structure or just do it by hand?
Oh, very good. Thank you, tutor. I had the slides before. I thought I had too many, so I deleted. First of all, you compute that you have like two, right? You're on the sigma u. You have is 2n dimension. You can just write down precise, very concrete 2n functions with n polynomials. You know it's very easy to compute the Poisson bracket because everything is very explicit. So you can write down n functions which are algebraically independent and their Poisson brackets are 0. That's first thing. So you know you have n Poisson commuting functions. Now, secondly, you try to integrate. You can solve the Hamiltonian flow of each one, and their flows are all I think there's a term by Arnold called quasi polynomials. So these are like when you solve a linear PDE, linear ODE, you know that the solution is like a polynomial type times exponential of something, right? So the flows are all of that type. Because this Poisson CGL property, you basically when you try to solve the Hamiltonian flow, you're just solving linear ODEs actually. You're solving linear ODEs. So your ODEs are all linear. So therefore you get complete integral curves.
My God, this is a very, very special case.
Very, very special.
Very, very rare, yeah.
Very rare, yeah. Well, if you look at this property of being a CGL, that's why it's nice to have a CGL here. If you look at this Poisson bracket, for example, if you try to look at the Hamiltonian flow of x1, you write down the vector field because you look at this because you just solve it successively. You solve for x1, the flow for x1. Once you have that, you solve for the flow of x2. Each time you're just solving linear ODE. Yeah. And then you get very concrete integral curves. But then I just don't know how to make use of that. I want to make use of that to say like you get some kind of Lagrangian foliation and so on.
Yeah, yeah.
And then the question is, how is that foliation related to the groupoid structure?
Right.
Yeah.
So the integral curves are holomorphic, not algebraic, are they?
Integral curves are holomorphic, but they are all of the form of polynomial times exponential of like constant times t. You know, like when you solve the linear equation with inhomogeneous linear equation, right? So we always get, right? We teach in ODE, it's always that type of solutions, yeah.
Yeah, Jiang-Hua,
yeah.
Different foliations.
Sorry, I cannot hear.
Can you hear me?
Yeah, who is this?
It's Iakovos. Androulidakis.
Sorry, cannot hear you.
It's Iakovos Androulidakis. Hi.
Oh, I cannot hear.
Iakovos. I can hear him. Maybe I can repeat the question.
Ah.
Iakovos, go ahead.
I was since Jiang-Hua mentioned foliations, I was wondering. I'm not very. I don't know these things very well, but I think in the case of CPN, the Brufati composition is actually the orbits of an action of a triangular matrix.
So Jakob's saying, since you mentioned foliations, he says in the case of CP1, Brujat decomposition. CPN, Brujat decomposition is what, sir?
Is the orbits of the action of triangular matrices.
The orbits of the action of triangular matrices.
Yeah, it's a singular foliation. You can, I think there is a way to see it like this. So I was wondering if these generalized Schubert cells have a similar description.
So he's wondering if you can generalize Schubert cells in using a similar description. Is that correct? Am I asking the question correct?
Yep. Thank you, Nikita.
The question is the generalized Schubert cells, whether they are in, you have the analog of that for CPN or other, you mean other partial flag varieties instead of full flag variety? Is that the question?
I think that was the question. Is that correct?
Maybe I think maybe the question was whether these are form a singular foliation of some kind. Is that right, Jacobus?
Yes, exactly. Yes.
Oh, you mean the decomposition into Schubert cell, general Schubert cells?
Yes, exactly. Yes.
Oh, they are, first of all, it's the disjoint union. And then that maybe then if you take the closure, so this is a disjoint union.
Right.
Now, of course, if I'm not sure whether I'm answering the right question, then if you take the closures, and then the closures, the geometry of the closures are very complicated. Even if you just have one copy of, just look at F1, just look at G mod B. Of course, this is a whole big business about Schubert calculus or Schubert. The singularities of Schubert varieties is rather complicated.
Yeah.
So if you take the closure of these varieties, what kind of, it's not a foliation, but it's a, singular foliation. What is, this certainly is going to be, they all have different dimension, but the way I have it here, this is disjoint union and each piece is smooth and no problem. But if you take closures,
I think singular foliation means more or less something like the where the leaves are generated by the images of some. You have a finite number of vector fields locally, such that if you look at their orbits, then you get the leaves of this foliation.
Yeah.
And and of course, these vector fields can be linearly independent in some places, and then you'll get open leaves, and other places you'll get smaller dimensional leaves.
Yeah.
Or for example, if you just take the orbits of a Lie groupoid or a Lie algebroid, that's an example of a singular foliation.
Right. Now this one, I'm not sure. Yeah. No, but these are. Wait a minute. I don't know. These are not orbits of anything. No, these are not orbits.
Yeah.
No, they are not like, yeah. So if you have a Lie algebroid, a Lie groupoid, as you say, the orbits of Lie groupoids is an example. These are not.
Yeah, I was just saying that in the case of CPN, the Schubert cells, they are the orbits of the action by triangular matrices.
Right. They are the orbits of B. Yeah.
So I was just something to think about. I mean, maybe it is wrong, but maybe this generalized Schubert cells, maybe one can think if something similar is going on. I don't know.
Oh, so the question is whether these are orbits of some group action.
Yeah.
I think they are not. Yeah, I understand your question now. I don't. I think they are not the orbits of. I mean, this Fn is like n copies of Bn, as I said somewhere that. But they are not the orbits of B action. No, then that will be product. No, not that orbit. Yeah, I don't know.
Okay.
Yeah. I think no. Yeah.
So Lou, I have a question.
Yeah.
So maybe I'm a bit confused, but if you have like
sorry, who is this? Is Rui?
Rui, yes. This is Rui.
Hi.
If you have like a law canonical Poisson structure and you look at the symplectic groupoid, it's algebraic in the sense that the symplectic structure is given by a polynomial Poisson structure.
Okay.
But the structure maps are not algebraic. They involve some exponentials.
Okay.
But you are saying that in the groupoids that you are getting, everything is algebraic, including the structure maps, multiplication, source, and target.
Well, right. As I said at the end, where is my end? Yeah, sorry. Here, the is actually a subgroupoid of this thing.
Right.
So the defining equation, this is given by the subgroupoid is as a submanifold is given by polynomial equations.
So why is it true that for log canonical you cannot have that, but you can have for these that are somewhat related also with log canonical?
maybe these ones aren't simply connected.
Oh, oh yeah, the fibers may not be, okay, it depends. Oh, okay, that's a very good point. I have a G, I start with a connected G. You see my OU actually is independent of the G because you factor out the B, so you factor out the torus. So there's no, so for all the different G with the same Lie algebra, but whether it's simply connected or adjoint type, I get the same OU. But this groupoid I construct depends on G. So I actually don't have only one. I have for each Lie group G, which has the same Lie algebra, of the same Lie algebra, I get one groupoid. Now, I think in a simply connected case, the groupoid, the fibers are not even connected, in some examples at least. But if you take the adjoint type, then the fibers are connected. At least in some examples. So I don't quite know the general answer. So yeah, so the fibers are not always connected. Does that? I know. So you are talking about. I know this in this paper by Lee and Ruppel, right?
Right.
Dylan.
Exactly. Yeah.
Yeah.
They
So
construct the symplectic groupoid there, but the source and the target map or the multiplication. Well, the source you can make it a projection, so you can make it algebraic. But right. Then the target and the multiplication, they involve exponentials. They are not algebraic.
Right. Now, but if you look at my the groupoid structure here, the inverse, for example, is it just take the inverse inside the group. If we look at this, yeah, here.
Right.
Here. You see, this is all. You see, everything is algebraic. If you look at the inverse, it's just inverse inside the group. Yeah. Yeah,
so
I know that there they take an exponential, but does that mean? But the symplectic groupoids are not unique, right? Does that mean that?
Well, they have the source simply connected one. They have the canonical integration in some sense.
Right. The source simply connected one has exponential, right? So it's transcendental. But don't they have an algebraic one as well?
Well, the space is just Cn, or C to the 2n, and the Poisson structure is algebraic. The symplectic structure is algebraic.
Right.
But the structure maps are not. They are, the multiplication of the target, they have exponentials.
Right. Yeah, but that's only one of them. Don't they also have an algebraic one?
I don't think so.
But can't you, in principle, have different coordinates in which things become algebraic?
Yeah, maybe in the...
Because I think your equations, they hold in affine spaces, but they're like opens inside there. I mean, it looks like you're using different coordinates.
I need to look at... I do have an example. So if the U involves only all different simple roots, I do have a log canonical Poisson structure. So my integration, I should compare
would be algebraic, your integration that you get there.
In my integration would be algebraic, so I should compare.
Yes.
Yeah, I definitely should compare. Yeah, that's another thing I had in mind. So they use the cluster structure. So for log canonical, they construct one, and for different cluster charts, then they try to match them together, glue them together.
By glue them, yes.
Yeah, by using these mutations. But here I have the base is also a cluster variety, but I'm just getting one, just a groupoid. Just once for all. I'm not gluing anything, but then I should compare. Yeah, if I use their procedure to apply their procedure to my example, do their gluing, I'm not sure I'll get the one that I have. I don't know. I didn't quite understand. Yeah, I don't understand the gluing there.
So the other question I have is are these integrable systems algebraic completely integrable systems?
What does that mean?
In the sense of Adler and von Morbach.
In the sense of what?
Adler and Van Moorwerk. You know, there is this theory of algebraic completely integrable systems.
Yeah, but I don't know what does that mean? Algebraically integrable.
Well, you have to, in particular, they're going to be linearizable on a Jacobian variety, and when you look at action angle coordinates, for example, you get as linear flows on Jacobian varieties.
Oh, linear flows.
Doesn't it mean that you need a spectral curve to start with?
Not necessarily.
But then the Jacobian of what?
Well, I mean, this is this theory where you look at expansions in terms of solutions in terms of meromorphic functions, and then you have to look at the complex times and whatever. I mean, there's a whole.
So
they are very special. Algebraic completely integrable are very special and very rare, like yours.
Okay, I don't know. Yeah, but I forgot to say that this is a generalization of the Kogan-Zelevinsky integrable system on double Broha cells. I don't know whether so Kogan-Zelevinsky wrote a paper where one of their results is to determine the symplectic leaves inside double Broha cells, but they also proved that on GUU. So when on GUU, you actually get an integrable system. So I'm just talking about a generalization of that. So where's the GUU? Yeah, here. So they proved that on GUU there's an integrable system, but they didn't try to solve the integrable system. So what I'm saying that integrable system can be, I can solve it very explicitly, but I don't know how to fit this into the existing terms. Completely solvable in the sense that I can write down the solutions. That's what I mean by completely solvable, but I don't know in other terms, what's the meaning, like algebraically integrable or, yeah.
Okay, thank you. Very nice.
Yeah, thank you.
So do we have any further questions still? Because if it's not the case, then I would say we thank Jiang-Hua once again.
Thank you.
And just a reminder, I think it was also written in the email that next week there's going to be no global Poisson. Instead, there's going to be a mini workshop on singular structures, I believe organized by Eva, with a lineup of exciting speakers. So check it out. And then 2 weeks from now, we're back at Global Poisson, and it's going to be Nigel Hitchen. So thanks for coming.
Thanks a lot, everyone.
Bye-bye.
Thanks.
Thank
you.
Bye.
Very nice. Thanks a lot.